Hello everyone. In this video, we will examine or begin to examine topic 9.4, resolution, and in particular, we will examine the size of a diffracting aperture and the resolution of simple monochromatic two-source systems. We will learn to solve problems involving the Rayleigh criterion for light emitted by two sources diffracted at a single slit. So, resolution is the ability of any imaging system to produce two separate distinguishable images of two separate objects. The idea is that we can resolve them if we're looking for them. You can tell them apart. And we're going to consider lots of different, there are lots of different types of resolution. You could talk about a resolution in a political system where you could resolve to do something about the government or whatever. But this kind of resolution is related to the concept of resolution that you hear sometimes when people talk about the resolution of their camera, the resolution of an image, or perhaps the resolution of their computer screen. In each case, what matters is whether you can tell whether different things are different from looking at it. And the instruments we're considering include things like eyes, cameras, telescopes, microscopes, etc. Now, resolution can be affected by many different things, but we are going to consider diffraction-limited resolution. This is a kind of limitation on resolution that is only due to the optics, and so this applies even if everything else is great. The kind of resolution that the Hubble Space Telescope fights with, or when they're trying to make images sharper, the diffraction of the light as it goes through the aperture of the telescope is the problem. It's what limits ultimately the resolution of those images. So, the general principle about whether you can resolve two things, or the criterion that we use, is known as the Rayleigh criterion. And it states that two objects can be resolved in the image if the central maximum of the diffraction pattern of one image is farther away than the primary minimum of the diffraction pattern of the second image. It'll take us a little while to unpack that, but that's the Rayleigh criterion, and in fact, that is a definition you should probably be able to rattle off on command. First of all, we are considering at this point resolving sort of two small things, or two small dots, point sources, from the perspective of the camera. We won't today consider sort of the complexities that come with resolving an extended image. So we're considering 2 point sources. And if you're far enough away to not be able to resolve them, then usually you're not concerned with the fact that they are extended in any way. Sources that behave truly like this include things like stars, which, although they are large, are so far away that they are completely diffraction limited, except for the very nearest stars. So, a star, for example, might give you an image that looks like this. You'll recognize that this is a simplification of the single circular aperture diffraction pattern. And you can see that primary central maximum, a primary minimum, that gap in the middle, and then a sort of secondary maximum right here. You can see that image. And the general point is that when you detect these two things on your imaging device, you detect these two intensity profiles, except you don't detect them separately. You detect them as if they lay on top of one another. Now, if they're far enough apart, you can easily tell there are two different objects here. This one on the left, and the one on the right. Okay? Whereas if we take a look at this third example over on the bottom right, you can see that the two red curves corresponding to the images of both objects, lay on top of one another. And as a result, what you actually detect is this blue curve. And from the perspective of your camera, that looks like a single image. So you can't tell that these two objects are different objects. And the point where they cross over, so the Rayleigh criterion refers to the point where you can just barely tell that they're different, is shown right here. That's known as just resolved. And it happens, as we said, when the central maximum, in this case of the right image, is directly over the primary minimum of the left image. So this is the very closest they could be where you could still resolve the two images separately. In real life, it's not too hard to get an example of sort of how this would work. If you have a piece of paper in front of you, I would invite you to do this. But draw two dots with a pen or a pencil very, very close together on a piece of paper. Very, very close together so that you can still see that they're two different dots, but as close together aside from that. Then hold them close to your face so that you can see that they're different. Then slowly pull that piece of paper away. What will happen at some point is that they will cease to look like two different dots and start to look like one. That's the point that we're interested in. That's the one defined by this Rayleigh criterion.